Good morning to all. Today we are discussing Theorem 9.33. Monotone sequence. Let sequence Tn be a sequence of bounded self-adjoint linear operators on a complex Hilbert space H such that T1 less than or equal to T2 less than or equal to etc. less than or equal to K, where K is a bounded self-adjoint linear operator on H. And suppose that any Tj commutes with K and with every Tm. Then sequence Tn is strongly operator convergent, that is Tn of x converges to Tx for all x belongs to H, and the limit operator T is linear, bounded and self-adjoint and satisfies T less than or equal to K. So the statement says that we are given a sequence of bounded self-adjoint linear operators on a complex Hilbert space H, and they satisfies T1 less than or equal to T2 less than or equal to etc. and less than or equal to K, where K is a bounded self-adjoint linear operator on H. And also given each Tj commutes with K and Tj commutes with every other Tm. So then we are going to show that sequence Tn is strongly operator convergent. That means Tnx converges to Tx for all x belongs to H. Moreover, the limit operator T is linear, bounded and self-adjoint and satisfies T less than or equal to K. That means the limit operator satisfies all the properties of sequence Tn. Okay, now let us go to the proof. We denote Sn is equal to K minus Tn. We know that each Tn is less than or equal to K, so we are considering K minus Tn and denote it as Sn. And also we know that K and Tn are self-adjoint. So their difference K minus Tn is also self-adjoint. That implies Sn is self-adjoint. Moreover, we can see that since each Tn less than or equal to K, K minus Tn is always positive. Okay, then we have to prove that sequence Tn is strongly operator convergent. That means Tnx converges to Tx for all x belongs to H. For this, first we prove that sequence inner product Sn square xx converges for every x belongs to H. And using this, we are going to prove the strong operator convergence of sequence Tn. For this, let us consider m less than n and Sm square minus Sn into Sm we are considering. Then taking Sm as a common factor, and this is equal to Sm minus Sn into Sm. Then just substituting for Sn and Sm. That is K minus Tm, which is Sm, minus K minus Tn into K minus Tm. Sm minus Sn into Sm. Then expanding this, we get K minus Tm minus K plus Tn into K minus Tm. That is Tm minus Tn into K minus Tm. So we get Tn minus Tm into K minus Tm. Then we are assuming that m less than n. Then we know that Tn minus Tm is positive because T1 less than or equal to T2 less than or equal to etc. So m less than n implies Tm less than or equal to Tn. So Tn minus Tm is positive. And again Tm less than or equal to K, and hence K minus Tm is also positive. So we get these two are positive and Tn and Tm commutes each other and commutes with K also. So we can say that Tn minus Tm and K minus Tm commutes. So using theorem 9.31, which states that if two bounded self-adjoint linear operators S and T on a Hilbert space H are positive and St is equal to Ts, then their product St is positive. And here Tn minus Tm and K minus Tm are bounded self-adjoint linear operators and defined on a Hilbert space H. Moreover, these two are positive and also they commute each other. So we can say that using this theorem, the product is positive. That means Sm square minus Sn into Sm is positive. The operators commute the product positive by this theorem. So the product is nothing but Sm square minus Sn into Sm. So here we get Sm square minus Sn into Sm greater than or equal to 0. That is here. And this implies, we know that Sm square minus Sn into Sm greater than or equal to 0 implies Sm square is greater than or equal to Sn minus Sm. and this implies Sm square greater than or equal to Sn into Sm. Again we are considering Sn into Sm minus Sn square. Sn into Sm minus Sn square, and just above we are taking Sn as a common factor, that is Sn into Sm minus Sn. Again substituting from Sn is equal to k minus Tn for Sm and Sn. So this is equal to k minus Tn into k minus Tm minus of k minus Tn, that is on simplification we get Tn minus Tm. So we get k minus Tn into Tn minus Tm, and this is also greater than or equal to 0 or positive because each of these two terms are positive. So product is positive since they commute as before. So we get Sn into Sm minus Sn square greater than or equal to 0. So we get Sn into Sm greater than or equal to Sn square. Then comparing these two or connecting these two, we get Sm square greater than or equal to Sn into Sm greater than or equal to Sn square. And again Sn from the definition of T1 less than or equal to T2. Comparing this, we can see that T1 less than or equal to T2 if and only if inner product T1xx less than or equal to inner product T2xx for every x belongs to it. And this can be extended to finite number of operators. So here we get, also we can say that T2 greater than or equal to T1 like this. T2 greater than or equal to T1 means inner product T2xx greater than or equal to inner product T1xx for all x belongs to it. So applying this for these three operators, we can say that inner product Sm square xx greater than or equal to inner product Sn into Smx x greater than or equal to inner product Sn square xx, and the last term equal to inner product Snx Snx because Sn is self-adjoint. This Sn, one of the Sn square is transferred to the second entry, that is we get inner product Snx Snx, and this is nothing but norm Snx square because we know that norm x is equal to norm x square is equal to inner product xx, and also we know that norm x is always greater than or equal to 0. So we get this greater than or equal to 0. That means inner product Sm square xx greater than or equal to inner product Sn into Smx x greater than or equal to inner product Sn square xx, which is greater than or equal to 0. So all these terms are positive terms. Okay. So from this, the above represented equation 1, we can see that inner product sequence inner product Sn square xx is monotone decreasing sequence of non-negative numbers. Already we have seen that this is positive. All these terms are positive. That is inner product Sm square xx and inner product Sn square xx are positive terms. And also m less than n means inner product Sm square xx greater than or equal to Sn square xx implies. Using these two, we can say that this is a monotone decreasing terms of or decreasing sequence because m less than n, but inner product Sm square xx greater than or equal to inner product Sn square xx. So we can say that these are monotone decreasing terms. So inner product Sn square xx is a monotone decreasing sequence of non-negative numbers. Always this is greater than or equal to 0 we have shown. So monotone decreasing sequence of non-negative numbers, and we know that they converges. A monotone decreasing sequence consisting of non-negative terms definitely converges. Then we have to show that sequence Tnx converges. So we are claiming that sequence Tnx converges. And we know that Tn is equal to k minus Sn. For this, it is enough to prove that sequence Snx converges. And also we know that H is complete. So we know that every Cauchy sequence converges. So it is enough to prove that sequence Snx is Cauchy. And from this we get sequence Tnx Cauchy and it converges. Okay. So we are going to show that sequence Snx is Cauchy. For this we are considering norm of Sn square Snx minus Smx. Before that we are going to introduce a relation result by using this relation 1. From this comparing the second and third terms, we get inner product Sn into Smx x greater than or equal to inner product Sn square xx. Then multiplying with minus 2, we get minus 2 into inner product Sn into Smx x less than or equal to minus 2 into inner product Sn square xx. Because multiplying by minus, inequality become reverse order. So we are considering by one we are saying minus 2 into inner product Sm into Snx x less than or equal to minus 2 into inner product Sn square xx. And also each Sj's all commute and self-adjoint that we are using in this next step. Okay, so we are going to consider the condition for sequence Snx is Cauchy. For this we are considering norm of Smx minus Snx. Here we are considering norm of Smx minus Snx square because we have to represent this in terms of inner product, and we know that norm x square is equal to inner product xx. For this we are using norm of Smx minus Snx square, and this is equal to inner product Smx minus Snx, Smx minus Snx, and Smx minus Snx can be written as Sm minus Sn of x. So this is equal to inner product Sm minus Sn of x, Sm minus Sn of x. Then we know that Sm and Sn are self-adjoint. So Sm minus Sn is also self-adjoint. Then this operator Sm minus Sn is transferred to the first entry and becomes inner product Sn minus Sm minus Sn square by using the self-adjointness of Sm minus Sn. So here we get inner product Sm minus Sn square xx. Then Sm minus Sn square is expanded by using the expansion a minus b the whole square. So here we get this is equal to inner product Sm square minus 2 into Sm into Sn plus Sn square of xx. And separating or splitting by using the properties of inner product. So this is nothing but inner product Sm square xx. Sm square xx minus 2 into inner product Sm into Sn xx plus inner product Sn square xx. And now we are using this result, that is minus 2 into inner product Sm into Sn xx less than or equal to minus 2 into inner product Sn square xx. For substituting here we are using this result. So this can be replaced by this middle term minus 2 into inner product Sm into Sn xx can be replaced by minus 2 into inner product Sn square xx, and then this equation becomes less than or equal to or inequality. So we get this is less than or equal to inner product Sm square xx minus 2 times inner product Sn square xx plus inner product Sn square xx, and getting minus 2 into inner product Sn square xx plus inner product Sn square xx, we get minus inner product Sn square xx. So this becomes inner product Sm square xx minus inner product Sn square xx. Also we know that these terms are terms of non-negative numbers, terms of monotone decreasing sequence of non-negative numbers. These are non-negative and monotone decreasing. Then we can say that sequence inner product Sn square xx is converging. Already we have seen sequence inner product Sn square xx converges, and we know that every converging sequence is Cauchy. So sequence inner product Sn square xx is Cauchy, and the difference of these Cauchy sequence are given in the right hand side. And also norm of Smx minus Snx square less than or equal to the difference of the terms of the Cauchy sequence. And also from this we get sequence Snx is also Cauchy. Since H is complete, every Cauchy sequence converges, and so sequence Snx converges. And we know that Tn is equal to k minus Sn. So Tnx is equal to k minus Sn of x, that is kx minus Snx. Since Snx converges, from this clearly we get Tnx also converges. Then, and this Tnx, this is for each fixed x. For each fixed x, sequence Tnx converges. So we can say that the limit is depending on the element x also, or the vector x also. So we can write Tnx converges Tx for every x belongs to H. Such an operator T can be defined. And that is defines an operator T from H to H, because T of x equal to Tx. For each x belongs to H, Tnx converges, and the limit is some vector in H, that is denoted by Tx. That is limit tends to Tn of x is denoted by Tx. So we can define an operator, well-defined operator T from H to H. Then we are going to show that this operator T is also bounded, linear, self-adjoint and T less than or equal to K. So, first of all, linearity. We know that each Tn is linear and T is nothing but limit n tends to infinity Tn of x. Since Tn is linear, T is also linear because limit and inner product as continuous functions also. Okay, so T is linear since each Tn is linear. Again, we have to show that T less than or equal to K. We are given Tn less than or equal to K for every n. And we know that limit n tends to infinity Tn of x equal to Tx. So definitely we can say that T less than or equal to K. Then next we are going to show that T is self-adjoint. And we know that each Tn is self-adjoint and the inner product is continuous. We can say that T is also self-adjoint because self-adjointness is inner product Txy is equal to inner product xty. And to prove the self-adjointness, we are using inner product also. So we say that T is self-adjoint since Tn is self-adjoint and the inner product is continuous because Tnx T is nothing but limit n tends to infinity Tn of x. So limit n is also a continuous function, inner product is also a continuous function. So we can interchange these two and from that we get T is also self-adjoint. Then we have to prove that T is bounded also. Sequence Tnx converges, that we have proved, we are shown here. Sequence Tnx converges and we know that every converging sequence is bounded. So we can say that sequence Tnx is bounded for every fixed x belongs to H. And we are going to use bounded inverse theorem. Sorry, uniform boundedness theorem. We are going to use uniform boundedness theorem. And uniform boundedness theorem says if sequence Tn is a sequence of bounded linear operators and for each x Tnx sequence norm Tnx is bounded, then T is also bounded. Tnx converges one, T is 1. Then by using uniform boundedness theorem we get T is bounded. So that is the end of this proof